Okay, so, oh, by the way, so I will have office hour this afternoon from 4 to 6. So feel free to come and we can discuss questions, whatever you want. So first, I will go through all the concepts, and then I will show you some examples like how to solve problems. Feel free to stop me, like you can just unmute and ask questions. It's easier for us to
Gee,
communicate.
will you be posting these notes after?
Yeah, sure. Yeah.
Thank you.
Okay, so now let's get started. So the first big topic is about vectors, right? Yeah, and so there are two basic operations. One is dot product or scalar product. Another one is cross product or vector product, right? You need to know how to do this kind of calculation, and also combine them two, you get this kind of a dot b cross a, something like that. These are very basic operations. And after that, we learned scalar field and vector field. So basically, to have a field, you need to have a domain, for example, like R3, or in this case, it's a plane, so it's a R2. So at each point, you assign it with, let's say it's like a number or a scalar, then it's a scalar field. If you assign each point with a vector, then it's a vector field. So in this case, so for scalar field and vector field, there's a, you can say there's a spatial dependence, meaning that you can do derivative. And there are three important operations known as like gradient, divergence, curl, right? So for the gradient, it's acting on a scalar field, and the result is a vector field. And the divergence is acting on a vector field and give us a scalar field. And the curl acting on a vector field and give us a vector field. So for these operations, you need to know how to do the calculation, and also you need to know what's the physical meaning and the geometric meaning. So for example, for the first one, for the gradient, it was tested in in the midterm one problem one, right? So basically, give me a scalar field, then we can calculate along which direction this scalar field is increasing or decreasing most rapidly at some specific point, or what's the changing rate along some specific direction at some point, something like that. And associated with this kind of operations, there are two important theorems. So first one is a divergence theorem, and another one is a Stokes theorem. And for the divergence theorem is nothing but a Gauss law we learned in 1B class. And it was tested also in the midterm one, problem 3, remember? And okay, so what is divergence theorem? It's nothing but this equation. So when we have a volume integral, so let's say the integration is integrated over a volume V, and the integrand is in this form, is a divergence of a vector field A, then we know it can be converted to a surface integral. And the argument in this case, sorry, the integrand is given by A dot ds. And the surface in this case is a boundary of the volume V. The boundary of a volume is a closed surface, right? Yeah, this is important. And usually we start from the right-hand side and apply the divergence theorem to solve problems, to convert this kind of surface integral to a volume integral. So in this case, we need to pay a special attention because in this, the surface must be closed. Otherwise, we cannot just apply this divergence theorem directly. Another similar theorem is the Stokes theorem. So basically, we have a surface integral in this case, and the argument, the integrand is a curl of a vector field A, and we can convert this surface integral to a line integral. right? So the integral, this line integral is integrate over a line, which is the boundary of the surface. A boundary of a surface is a loop, right? So the structure you can see quite similar to the divergence theorem.
But that's an open surface, right?
Yeah. In an open surface. By the way, if your surface is a closed surface, if it's a closed surface, meaning that omega is the boundary of some volume, right? A closed surface must be a boundary of something, right? In this case, a boundary has no boundary, meaning that the boundary of this guy, partial v, which actually is zero, meaning that it's always give us zero. I think this is one of your homework, or yeah. Okay, so yeah, there's another theorem. It's like a Green's theorem. So this is just a special case. You can regard it as a special case of the Stokes theorem or the divergence theorem. So for example, from the Stokes theorem, if we assume this like this surface is within the xy plane, then meaning that this ds is nothing, this infinitesimal area element is just dx dy, and the direction is z hat, right? And if we assume that it's a, vector a, to be in this form, basically it's p, q, 0, 0 meaning that the z component is 0, and then plug in to this guy, we will get this Green's theorem. So it's just a special case. Okay, so this is for vector part. Of course, there's another important concept associated with what we talk about here, which is the conservative force. Basically, by the way, this is also tested in the midterm one, right? Give me a force, like you need to tell whether this force is conservative or not, right? So there are several ways to do it. First one is calculate the curl of this force. So if this curl del cross F equal to 0 on the whole domain, then it's a conservative force. So here I wrote down an example, which is from this problem, midterm problem. So there is it's kind of the z component is 0. There are only two components. So the x component is minus y divided by x squared plus y squared, and the y component is x divided by x squared plus y squared. So we notice that there's a singularity at the 0, 0 point. So even though you calculate the del is 0, but it's only true at this region. Actually, this curl is non-zero at the orange, at this 0, 0 point. It's actually a third function. If you remember the solution we posted on the CCLE, yeah. So in this case, this F is not a conservative force, right? And the second way to determine whether it's a conservative force or not is by looking at the loop integral. So if we can find a loop along which this F dl is non-zero, then it's not a conservative force. Remember, for this force, there's a loop. As long as this loop encloses this 0, 0 point, then the result is 2 pi, I think, or minus 2 pi, depends on the direction of this loop. It's non-zero, meaning that indeed this F is not a conservative force. And there's another way to determine whether this is a conservative force or not, which is by looking at the force, like whether this force can be written in this form. Del phi, phi is known as the potential or potential energy, whatever. And the phi, if phi is defined on the whole domain, then F must be a conservative force. So for this force F, you may say, okay, it can be written as like arc tang y divided by x. But this guy is not defined on the whole domain. You can see, yeah, there were also singularities. This is nothing but, by the way, this is nothing but like a theta, I think. Yeah, right. Yeah, it's EL defined at orange as a 0, 0 point. Okay, so these three like conditions it must be equivalent, right? So for example, let's look at the first one and the second one. They are related by this Stokes theorem. So basically, for example, if the curl of this force is 0, then this loop integral must be 0. And also let's look at the first and the third one. If your force can be written in this way, this must be 0 because the curl of a gradient is 0. Right? So any question?
A quick questions. What did you mention for the Green theorem? I didn't catch that part.
Oh, so what I said for the Green theorem is like a Green theorem is just a special case of Stokes theorem. So if we assume the area we're integrating over in the Stokes theorem is within the XY plane, then the ds is nothing but dx dy, and the direction is the z hat. Oops. Sorry about that. Waiting for a second. Okay. Right. So if we assume that the A vector A is in this form, PQ0, then you plug in this Stokes theorem, just tells us this equation, which is known as Green's theorem.
Okay, I see it's just a derivation.
Yeah, it's just derivation.
Thank you.
Yeah.
A quick question.
Uh-huh.
For 3 here, case 3, how do you think about finding a phi that satisfies that?
Oh, right. Usually, okay, so I would say the most common one is use the first one. And if you find there's a singularity, meaning that the domain is not simple connected, then of course for 2-dimension, if there's a point that is singularity, that is singular, then it's not simple connected. Then we just need to choose a kind of a, you know, what's this? Like the loop around that point and calculate this kind of a loop integral. I would say the first one, the second one are most common used to verify whether the force is conservative force or not.
Okay.
Yeah, I mean, sure. There's a if you calculate, yeah, I would say it's much easier. Yeah. For the third one, you need to do some integral and to find whether you can kind of find this phi or not. But if you can find a phi, then I'm pretty sure the first one is much easier than your third one. So.
Got it. Thank you.
Okay, so the next topic is about integration, right? So in this part, you need to know how to calculate the area of some surface and versus the volume of some shape. So it's tested in the midterm 1 problem 3, right? For example, you have you have some curve, some area under this curve, and you revolve this area around some axis, you get some shape, then you can calculate the area, stuff like that. I will show you an example later on, so you can see how to calculate. So the next topic is about complex numbers. So here I wrote down several points that is important, I think. The first thing you need to know is kind of how to convert a complex number between different forms, right? This is also a problem in your midterm 2, the Cartesian form and also polar form, right? And also you need to know how to find the roots, like for general complex number. It's also one of the midterm problem. Another thing that's not tested in the midterm is the geometric meaning. Okay, so I guess the most important thing is what's the physical meaning, what's the geometrical meaning of this guy, absolute value of z1 minus z2. So we know that in the Cartesian coordinate, xy coordinate, each complex number stands for a point, right? And then the absolute value of this guy stands for the distance between those 2 points. And for example, one of your homework, I think, this is just ellipse. And another thing you need to know is the convergence problem. So basically, given a series like this, ask you what's the value for z, that this such that this series converge. Then you only need to construct a value rho by doing like this, right? Like a limit n goes to infinity, an plus 1 divided by an and the absolute value. And we want this guy to be smaller than 1. Then we get the regime of this complex number z. Okay, so this is the complex number part. The next part is about the Fourier series. I'm pretty sure you are familiar with this part because we just, I mean, the midterm 2 just like two weeks ago. So for this part, you need to know the formula. For example, let's say I have a function which is given like from A to B is given like this. And then I tell you the period is B minus A, meaning that the function on the whole axis is like this. You just repeat this, right? Then I ask you to do a Fourier series expansion. Then, so we know it's given this form, right? A naught divided by 2 plus an cosine. The coefficients, you need to be careful. In this case, I mean, in generally speaking, it's just a 2 pi divided by the period. In this case, it's b minus a and times n and x. Okay, so and the same similar stuff for the bn and the sign, and also the formula for an and bn. Yeah. So the formula given in the textbook is a special case. It's like assume the function is given from minus L to L. Then in this case, the coefficient here is 2 pi divided by the period. In this case, is 2L, which is pi over L. Meaning, so this is the reason why you really have like cosine pi over L and x, things like that. Okay, of course you can expand this complex function in general using this kind of in terms of exponential ix. And or similarly, the coefficient here is the same as what we have in the cosine and the sine. And this expression for the coefficients is a little bit different. So first, we have a factor 2 here in the a and bm. There's no factor 2. And also there's a minus sign. Yeah. So the next thing is the symmetry. Yeah, by the way, it's tested in the midterm, right? Yeah. So if the function is a even function, is symmetric around the y-axis, then only cosine term survives, and the bn equal to 0. And if it's an odd function, then the an is 0, and only sine terms survives. Yeah. So if the question asks you to do a cosine Fourier expansion, then you know that the function must be an even function. So another thing you need to know is the Dirichlet theorem. It's also tested. So basically the question is like, we know that every function, every periodic function, we can do a Fourier series expansion. And now the question is, to what value the series will converge at this jump point? For example, assuming this point corresponding to A, this point corresponding to B, then this theorem tells us the series will converge to the middle point of A and B. So basically it's A plus B divided by 2 at this x0 point. So there's also another theorem. Yeah, there's so many theorems. So Parseval's theorem were known as completeness relation. So this relation tells us the relation between the average of the function. Oops, there's an L. Within one period, and the coefficients of the Fourier expansion, an and bn. By the way, this is nothing but v dot v equal to v1 square plus v2 square plus vn squared plus dot dot dot. If you regard this function as a vector. Right. So any question about this part? Okay, so I think I covered most of the important points. Of course, because there's a time limit, so I didn't cover all the points, all the stuff you learned in class. It's impossible. I mean, yeah. So here I will show you some examples and show you how to solve problems and something you need to be careful about. Okay, so let's look at the first exercise. Let's go through these problems together.
Excuse me, G.
Sure.
Someone has a question in the chat.
Oh, okay. So yeah, Azure needs a. Yeah, right. So, right, this theorem just usually used to calculate this kind of evaluate the like n equal to naught from finitism. I don't know. I just write some random. What's this guy and stuff like that. So okay, because you ask this question, let's do the last problem first because that's related. Oh, oops. Okay. Yeah, this one. I didn't choose a very complicated example. Instead, I choose actually a very simple one because I think the purpose is to illustrate how to solve problems. Like I think as long as you can solve simple problems, then if you have enough time, you can always solve complicated problems. Okay, so whenever you give a function, it's always good to draw the picture, right? To get some intuition. Yeah, human beings were always more sensitive about pictures. It's like this: 1 minus 1, right? L minus L. So we notice that it's an odd function, and then you should know if the question asks us to do a Fourier series expansion, then it must be sine stuff, like sine, right? Okay, so first question show this guy can be written in this way. It just tells us do the Fourier expansion for this function, right? And because here I wrote down all the details, because it's an odd function, so the an vanish, right? So only like a sine terms survive, and it's bn. Bn equal to according to the formula is written in this form, and because this guy is an odd function, sine is also odd function, so we can write this guy as 2 times 0 to L. And then fx becomes 1, and you do the algebra quite easily, and you get something like this, right? Here I just skip some algebra stuff. Yeah, if you have difficult time kind of following these kind of steps, welcome to my this office hours. I can show you all the steps. So anyway, we got this Bn equal to this guy. And so plug in, we got the expansion. And we notice that if n is even, the coefficients vanish because 1 minus 1 is 0. So only when n is odd, it's non-zero. So I can rewrite my coefficients like by setting n equal to go to n plus 1, and the summing originally is from 1 to infinity becomes 0 to infinity, and the n becomes 2n plus 1, and this 2 times this guy is 2, right? 2 times 2 is 4, and the n is replaced with 2n plus 1. Some tricks. Yeah. This is nothing but this, what we need to prove. Any question about this part? Okay, right. So the second part asks us to evaluate this guy. So this guy is nothing but, you can write in terms of this series, right? So to evaluate this guy, we notice that it looks like the coefficient of my series, but if I can square my coefficients, basically if I can square my Bn, so we have a hope to get something like this. Then we recall that in Parseval's theorem, there's something like a Bn squared, right? So we can apply this theorem. So on the left-hand side, we can evaluate the average of this function within one period, which is given by 1. The calculation is also straightforward to L and minus L to L. And because you're calculating the absolute value of of this function f, remember f is 1 or minus 1. So absolute value is always 1. So 1 dx, which is nothing but 2L divided by 2L, which is final result 1. On the right-hand side, we know an is 0. So we only have the last term. So it's 1/2 times the summation from 1 to infinity and the square of the of the Bn. Remember, Bn is given by this expression. And yeah, you square it. Similarly, only n equal to odd, you have a non-zero value. So kind of similar stuff we did before. And this n becomes 2n plus 1 and becomes factor 4, and simplify your results. You get this guy, and the left-hand side equal to right-hand side, we get this guy equal to 1. So this tells us the final result is pi squared over 8. So there's a question, what if Bn and An are both non-zero? So in that case, I mean, then the question won't ask you to evaluate only Bn, right? Then there must be words apart from the An square, something like that. Yeah, so basically my point is, whenever there's a question, ask you to evaluate this kind of summation of this kind of series, then you should be able to use this theorem. Otherwise, you can set your x to some specific number and get the result. That's two ways to get this result of this kind of summation. So okay, so there's some tricks about the boundary one. That is because so in this step, your n must be 1, 3, 5, stuff like that, right? Now, in the second step, I replace my n with n plus 2, n plus 1. So when n equal to 0, I get 1. And n equal to 1, I get 3. And n equal to 2, I get 5. This is the reason why in the second line, the n start from 0 instead of 1. For the part 2, it's okay. So I mean here, it's because your Bn there's no B naught, right? Only A naught and An and the B naught. Sorry, Bn. B naught, there's no B naught. B naught is 0 because you know, you look at the you look at this expansion, this Bn, the n always start from 1. Okay, so I think I have only 7 minutes left. So let me go through at least one more problem. And, okay, so let's look at this problem together. So basically we need to evaluate this surface integral. Yeah, is r dot n hat d sigma over the surface of a cylinder x squared plus y squared equal to 1. And the region, like the z is from 0 to 3, right? And r tells us that r is x, y, z. And hat n is a normal vector of the cylinder pointing outwards. So here I wrote down some steps you can follow. Basically, first, for this kind of problem, usually you need to visualize the problem, like visualize the surface. In this case, is a cylinder, quite easy. So x squared plus y squared equal to 1 is a cylinder with a radius 1. And this is from 0 to 3. So the height is 3, and like this, right? And so which theorem we need to use in this case is the divergence theorem, right? divergence theorem, because we have a surface integral and we can convert it to a volume integral. And because the reason why we want to convert it to a volume integral is because we notice that the del R is a constant. So it should help us to do the calculation. They can simplify our calculation. Another thing is whenever you apply this kind of theorem, you need to check the condition, check the assumption. So to apply the divergence theorem, the condition is the surface must be closed. In this case, the surface is not closed because this surface doesn't include the top disk and the bottom disk. So let's here I wrote down all the steps. So you can see what I'm doing here. Basically, starting from the original integration, the surface is a cylinder, and then to make the surface close, we need to add the top disk and the bottom disk. So omega 1 is stands for the top disk with the normal vector pointing up, so the hat, and the omega 2 is the bottom disk with a normal vector pointing downwards, so it's minus the hat. And so a cylinder plus omega 1 plus omega 2 is in this case is a closed surface. But to make this is an equal sign, you need to subtract omega 1 and omega 2, right? So we combine the first three integrals, we get a closed surface integral. And this guy, we can apply the divergence theorem. We get a volume integral, like what I said before, this guy is 3. And we there still subtract omega 1 and omega 2. And this is nothing but the 3 times the volume of this cylinder. And you can also do this surface integral omega 1 and omega 2 easily. So the volume in this case is easy. It's like the area of the disk, which is pi, times the height. Height is 3. So it's 3 times pi times 3, right? And for this omega 1, notice that omega 1, the z is always 3, right? So z is 3. By the way, r dot z is x, y, z dot 0, 0, 1, which is z. So z equals 3, so this is nothing but 3 integral of omega 1, which is dx dy. So this is the area of the disk, which is pi. So this is the reason why there's a minus 3 pi. And this is 0 because z is 0. And finally, you get the final result, you get 6 pi.
G, what in the problem told you that the surface wasn't closed? Because it shows like we kind of closed.
Okay, so because, okay, that's a very good question. Okay, so it's because there's a condition x squared plus y squared equal to 1. For example, for a point within the disk, the radius is smaller than 1, it's not satisfy this condition. So to satisfy this condition, the area we're integrating over only contains this, like the surface without the disk.
So if it said less than or equal to 1, like then.
Right. Okay, so if we say, okay, if we say this guy is less or equal to 1, then it's unclear because this no longer stands for cylinder. It's a cylinder including all, it's a volume, it's not a surface anymore, right? If you want to say, okay, you would say, okay, the surface is, oops, x squared plus y squared equal to 1, and they within this regime, and also x plus y squared smaller than 1 with z equal to 0 and z equal to 3. So this one stands for the bottom disk. This one stands for the top disk. But this one only contains the cylinder mechanism. Yeah, is Paul here?
Yeah, I'm here.
Okay, nice. I can make you the whole co-host, and you can continue.
Okay.
So you guys release solutions to all these problems, these exercises?
Yeah. I will post it on the CCLE so you can take a look and yeah. Wait. Let me stop sharing first. Kind of. Where's the? Yeah, I think. Okay, let me make you.
Okay. Are you gonna keep recording?
Yeah. I will. I guess I will just mute myself and then.
Okay. Okay.
Weird. How to do it?
All right.
I think you can sharing. I can work on this co-host.
Okay. So the way I'm going to present the rest of the material, I think it's also going to look like a cheat sheet for you. So hopefully that helps. Okay, so then you've learned about Fourier series. We go to the case where the periodic function is no longer periodic, or you can think that the period is infinite. So you just have some function. Then you get the Fourier transform. Or am I sharing? I'm not sharing. Am I sharing? Okay, maybe I'm not sharing.
Yeah, we can't see your screen. Maybe you can, yeah, redo it.
Try again. So, okay, so, okay, good. So the Fourier transform is defined as follows. Transform. G of alpha, that's the transform of the Fourier.
Yeah, we still can.
Still cannot see it.
Yeah.
Oh my God.
It's weird.
It says you've started screen sharing, but we don't see your screen. It's still just black. Oh, it changed right now, but we still can't see it.
Oh, I see why. Yeah, it was working earlier, right? Okay, then I'll join the meeting from my iPad and then do that. So give me a few minutes. 957-266. Okay. Yeah. Can you make my iPad host as well? Can you make my iPad host as well? Live chat. Oh boy. Um, okay. All right.
Yeah, we can see it now.
All right. Okay. All right. So the Fourier transform is 1 over 2 pi integration from negative infinity to infinity f of x e to the negative I alpha x d alpha. So this is the Fourier transform of f of x. And you can transform back. So this forms a Fourier pair g of alpha e to the I alpha x dx, d alpha. Right, so we have that. I think the kind of problems you can have is just compute the Fourier transform. So these are just do some examples of functions that are that you've practiced in homework. So, okay, so then if f of x even, then you can do Fourier cosine transform. Yeah, so I'm gonna write these down. So this will be like a cheat sheet for you. So instead you integrate from 0 to infinity only. Sorry, subscript should be c. F of x cosine alpha x dx. And then you can transform back. Again, integrating from 0 to infinity, g of c cosine alpha x d alpha.
Excuse
So-
me, for the
yeah.
Fourier transform before, you set both sets as d alpha.
Oh yes.
So
This
which
is a
one is
poorly written
dx.
x.
Yes, thank you.
Sorry. Yeah, very good. So then if f of x is odd, you have the sine transform, which I'm just going to copy paste. So the only thing that's changed is you can change the subscript from c to s, standing for sine, and then the cosines become sine. Right. So that's it. That's it for Fourier transform. Okay, so if a question says compute the Fourier transform of f of x, do we solve for just g of alpha or do we solve for g of alpha, then plug it into a second integral? Just solve for g of alpha. Yeah, and if the question says represent f of x using its Fourier transform, then you write down the second thing as well. So like, okay, so g of alpha is the Fourier transform of f of x, and then if the question asks you to find the Fourier transform, that's it, find g of alpha. Yeah, and then if the question asks you to write f of x in terms of g of alpha, then you write down the second line. Okay, so that's that. And then for these For transformers, also have the Parseval theorem. Which is that when you integrate over the absolute value squared of f of x, it's equal to the integration of g of alpha squared with some normalizing constant 1/2 pi. So that's it. Okay, so that's, I think this is straightforward. You just plug in functions and you do the transform. Then the next thing is Laplace transform. Right, so I like to write it as in this form. So the Laplace transform of the function f with the variable p is integral of 0 to infinity e to negative p t f of t dt. Right. So then you can do a bunch of Laplace transforms of familiar functions, exponentials, sines, polynomials, etc. And then how to find inverse. Right. There are basically two ways. One is you just look up the table. The table at the end of the chapter. The other way is to use convolution. So how do we use, what is convolution? So first we define what it is. So the convolution of f star g is integral from 0 to t, f of t minus tau, g of tau, d tau. Now, the nice thing about convolution is that the Laplace transform of the convolution is the product of the Laplace transform of each function. Right. So in a problem, you might be given this. So you have a product of two factors, and you want to find the inverse transform of this. You know the inverse transform of each factor. So then the Laplace transform of the whole thing is the convolution of f and g. So this is yeah, so that's nice. And then there's another technique that you would use is partial fraction. So how do we do that? How much time do I have? Oh, boy. Partial fraction is so let's say you have, okay, specify example. So if you have c over p plus a, p plus b, right? And I wanted to write it as sum of two things, each one just with one factor of the p plus a or p plus b. So how do we do that? So you find the common denominator. Right? Basically you're solving for a and b. So you first assume it can be separated into these two two terms, and you let a and b be some general things that you solve for. So you find the common denominator. This becomes a p plus b plus b times p plus a. So this is p plus a, p plus b, a plus b, p plus a minus a plus b. Sorry, no, ab plus b a. Right. So then you equate this to this. So it must be that a plus b is 0 and ab plus ba is c. So solve for a plus b. Not a plus b, but solve for a and b. Yeah, so that are just exponentials, and much easier to do. So these are the three techniques that you would use to find inverses. Okay, then the next thing is we use Laplace transform to solve differential equation, right? I think that's the main thing that we learned from in this class. Okay, and the type of differential equation we get is usually linear. So it will look like something like this: a0y plus a1 y prime plus a2 y double prime plus da 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 equals f of t. Okay, and then the f of t, and then the general strategy is to Laplace transform both sides. Okay, so y becomes big Y. Y prime becomes py minus y0. Y double prime becomes p squared y minus py0 minus y0 prime, y0 prime. And then y nth derivative in general is p to the n y minus p n minus 1 y0 minus p n minus 2 y0 prime minus all the way to y0 of n minus 1. Okay, so we can that's the Laplace transform for the left side. And then so so the left-hand side becomes a polynomial of p times big Y. And the right-hand side is just the Laplace transform of f. Okay, so that means you can solve for big Y to be 1 over that polynomial times L, the Laplace transform of the right-hand side. Okay, this thing has a name. This 1 over polynomial is called the transfer function. Yeah, and so finally, little y, which is the original thing we're trying to solve, is the inverse transform of this transfer function. So this transfer function, it is denoted as t of p times times the Laplace transform of f. So that's your solution. And the way to find the inverse transform, we just went over it previously, right? You look up the table, or you find the inverse using convolution, or use partial fraction. And then that's your solution.
To
Yeah.
find the inverse, you can't just straight up look up two of the inverses from the table and multiply them, can you?
No. Right.
You'd have to use convolution if
Yeah,
they're like product.
Can I scroll up a bit? Oh, is it too late? Oh, there's a bunch of questions. Okay. Okay, so I think there's a typo in the Fourier sine cosine transforms. Something. Should it say g of alpha? Yes, it should say g of alpha. Okay, so I'm gonna upload this note at the end. So it's good to get every little detail correct. Okay, so this thing, the red arrow means they're equal. Okay. Yeah. So here we are. So far so good. Okay, so since we talked about convolution, actually Fourier transform also has convolution. So it's the same convolution, but in different contexts. It might look a little bit different. So in the context of Fourier transform, F1 x star F2, well, F1 star F2 of x is integration from negative infinity to infinity, F1 of x minus y, F2 of y, dy. So that's also convolution. Nice thing about convolution is that so G1 alpha times G2 alpha, this is the product of the individual Fourier transforms of F1, F2. This is the product is the Fourier transform of the convolution. And if you run the argument the other way, the convolution of the Fourier transforms is the Fourier transform of the product. There's no one. So convolution and product are like dual to each other. Okay, so since we talked about convolution, it's also nice to write it down. Okay, so that's all about Laplace for now, and then we introduce this new concept, the Dirac delta function. Okay, so I like to think of its definition. So start with its definition, that is. So delta of x minus x0 is 0 whenever x is not equal to x0. It's equal to infinity, so it has a spike at x equals x0. And then the second property, it has unit area. Okay, so that means whenever you integrate over the delta function, it's equal to 1 if your interval includes the spike, and it's 0 otherwise. So interval is outside the spike. So that's the definition of delta function. And how do we represent this? Representations. There are a bunch of representations of Dirac delta function that you can find on the internet. The ones I'm going to list here are more relevant. So let's say you have a Gaussian e to the negative x squared over epsilon squared with some normalizing factor. And in the limit epsilon goes to 0, this becomes the Dirac delta function. So this is like what? This is a Gaussian function such that you let the width becomes less and less while maintaining the area being 1. So when epsilon goes to 0, it has 0 width, but the area is still 1. Okay, 2. So this is limit n goes to infinity, n times e to the negative nx. So x greater than 0 or 0, and x is less than 0. So this is, we're approximating a delta function with this exponential decay. Okay. So as n goes to, so n, 1 over n is like the width, again, like the width of this exponential decay. And as n goes to infinity, this width becomes shorter and shorter, and the area is still 1. So that's another representation. Or you can think of it as a square function. So again, limit epsilon goes to 0. It's equal to 1 over epsilon in a small interval, 0 otherwise. So this is just a top hat function that has width epsilon and height 1 over epsilon. You let epsilon goes to 0. Yeah, so these are different ways to think about Dirac delta functions. Okay, so what are some properties of this thing? Well, if you integrate it along with some other function, you just pick up the function evaluated at that peak. But this is true if only your interval includes that peak. Otherwise, it's 0. And then what are some other properties? The Laplace transform, since we talked about Laplace transform, is e to the negative t0. This is true if t0 is greater than 0. Okay. 3. Okay, so then delta x minus x0 is the same as delta x0 minus x. So if you flip the signs of the argument, it doesn't change anything. Like delta f of x is the same as delta negative f of x. Doesn't change anything. Okay. What else? So delta of g of x. So now it's some function of x, delta of some function of x. So you first find all the zeros of g of x. So you sum over x0 such that g of x0 is 0. So you find the zeros of the function g. And this is delta x minus x0 over the absolute value of the derivative of g evaluated at x0. Yeah, maybe we. How much do I have? Okay, so like an example, delta of x squared minus 1, for example. Okay, so there are two zeros of this x squared minus 1 equals 0. Means x equals plus minus 1. So delta of x squared minus 1 is delta of x minus 1 plus delta of x plus 1. Now divide by the derivative of x squared minus 1, which is 2x. And make sure you take the absolute value. That's the example. Okay. And then we have finally derivatives of delta function. If f of x, delta prime of x, delta prime, say x minus x0. This is if you take the derivative, you do an integration by parts and get ddx of f of x, sorry, negative ddx of f of x times delta x minus x0. So whenever you get derivatives on delta functions, you do integration by parts until there's no derivative on the delta function. In general, if you have the nth derivative, this is so you do dd x to the n f of x delta x minus x0. Yeah. Actually, this is not the most simplified thing I can write, right? So what is the derivative? What is this integral? Well, this is just negative f prime evaluated at x0. And then similarly for 6, this is just negative 1 to the nth power, nth derivative of x, nth derivative of f evaluated at x0. Oh, sure.
Excuse me, for the previous example, I think you need to plug in x equals to plus or minus 1 at the denominator.
So in here you're saying, right?
Yeah.
So since it's a sum, for the term that has x minus 1, you plug in 1 in the denominator.
Mm-hmm.
For the term that's x plus 1, you plug in minus 1 in the denominator. Okay, so let me write that down.
Thank you.
So this is delta x minus 1 over 2 plus delta x plus 1 over negative 2 absolute value. But so it's still 2, but because I plugged in x equals negative 1, so it's negative 2 absolute value of that. Is that okay? Okay, so in the 1 over 2 pi is in the Fourier transform, so it shouldn't be there, right?
That was for the convolution of f and g dot g from like above.
There's no, it's still there. This is the annoying thing that about the convolution of Fourier transform. You have this factor.
Oh,
of
sorry.
1/2 pi.
I was talking about like the one below where it's like g star g is equal to the Fourier transform of f and f. There's no 1/2 pi.
Let's see. Is it?
Because in the homework problem, we
There's
we
no-
proved
oh, yeah,
exactly that.
Yeah, yeah. There's no. Yeah. Okay. Yes. Where would this convolution be helpful? Is that your question, Elijah? Okay, I'm not sure when you asked that, so I can't answer that. Oh, when do we need convolution in Fourier transform or Laplace transform? Yeah, so if I guess it's all for finding inverses. Right? So for Laplace transform, you find the inverse of this whole thing using convolution. So let me write it down more explicitly. So so you know inverse of f, and you know inverse of, well, okay, not f, big F. Inverse of big F. You know inverse of big G. So what is the inverse of fg? Well, it's the convolution of f star g. So this is where convolution is useful in the Laplace context. Now in the Fourier transform, it's similar. So if you know the Fourier transform of one, let's say, okay, so you know the Fourier transform of f1 is g1. Fourier transform of f2 is g2. Then the Fourier transform of f1 times f2. This may not be easy to do, but you know it's the convolution of g1 and g2. So that yeah, so the in terms of problem solving, this is the way that it's useful. Yeah. Can I do an example? I'll do it in the end, I think, if people are staying. Okay, but I want to finish this note. Okay. Oh boy. Okay. All right. So we talked about Laplace transform and we talked about delta function. So this one special kind of problem is you solve these kind of differential equations. But the right-hand side is a delta function, right? So and then a lot of times you're given an initial condition. That all the initial conditions are 0. Okay, so then y is the transfer function times e to the negative p t0. Okay, so then so then what is y? What is little y? Okay, so let's say the Laplace transform of, suppose the Laplace transform of y hat is this transfer function. So it's like you're solving the differential equation without the delta function. Then the Laplace transform of y, oh sorry, y hat. Okay, so this is y hat of t, but y hat of t minus t0 is t of p times e to the negative p t0. Okay, so the solution y of t is this y hat t minus t0. So y hat is solution to differential equation a naught y plus a1 y prime plus dot 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 equals 0. And then with the delta function in place, you just shift the argument of y hat to t minus t0. So this I guess is just application of convolution. It's nothing new here. Everything we just said in this section can be derived from convolution in the properties of delta function and Laplace transform. Okay. Okay, so then the final thing I'm going to say is higher dimensional delta function. Okay, so you can write, so this is now a vector minus r naught. So okay, so r as a vector minus r naught, which is still a vector. This means delta of x minus x0, delta times delta y minus y0 times delta z minus z0. So it's a product of 3 delta functions. And so in Cartesian, it's this form, and in spherical coordinates, it looks the same, but you have a factor of 1 over r squared sine theta in front. In spherical, and 1 over r, delta r minus r0, delta theta minus theta 0, delta z minus z0 in cylindrical. Okay, so to give you a little bit of motivation of why this is true, I'm gonna say this. So in general, if you have a general change of variable, say x, y to uv, then the delta function in x, y variables is equal to the Jacobian times the delta function in the r minus r in the new variable, not r, so uv variable. So Jacobian is this thing, uv from the beginning of the quarter. This is partial u partial x partial u, partial y, partial v, partial x, partial v, partial y. Okay, so you can use this to understand why we have these factors in front. Right,
All right,
these are
is it-
precisely the Jacobians.
Is it 1 over the Jacobian? Mm,
Did, uh, okay, I think that's a different saying. Well, okay, so the usual way we define Jacobian was J is x y over uv, usually defined as this. Okay, so okay, maybe let me write it as that, then it's less confusing. But this thing I wrote here, the top and bottom have to flip, and so this is du. So this is dx du, dx dv, dy du, dy dv.
thank you.
Yeah. Okay, so that's and so that's it. Oh, and then there's a special case that you have to remember. This is important. That the divergence of 1 over r squared in the r direction is 4 pi delta r. This is a special case because yeah, I'll write down the two special cases first. So this is also delta of r. So naively, if you I think this is one of your homework problems, right? If you do the naive calculation, you should get 0 everywhere. But actually, it's non-zero. Actually, it's infinite at the origin where r equals 0. And the way to see this, you have to do it as the lecture did, where you use Gauss's law and all that to prove that. So these are the special cases where when you take the divergence or the Laplacian, you get a delta function instead of the naive 0. Yeah. Okay, so that's all the materials that you've learned so far. I've already 15 minutes over time. Okay, so then I guess an example of convolution with Fourier transform. So what's something that's easy to find a Fourier transform of? I don't have to solve something. Okay, let's say we have is it's a top hat function. So zero elsewhere. Okay, and then what is the Fourier transform of this? I think it's some constant times sine alpha over alpha. Yeah. Okay, and then we have another function. Let's say it's what is another function that's nice that can be Gaussian, let's say, e to the negative x squared. Okay, so the Laplace the Fourier transform of this is square root pi e to the p squared over 4, negative p squared over 4. Okay, so now or alpha pi, this constant is pi. Alpha is not a constant. Alpha is it is the variable. Okay, so I guess now the question is, what is the Fourier transform of f1, f2? Right, so this is equal to negative to infinity f1, f2 e to the I alpha x. Negative I alpha x dx. Okay, so then let's not worry about the constant factor. I'm not sure what is it, so I wouldn't worry about it for now. So this is just a show of principle, right? So this Fourier transform is, well, you only integrate from -1 to 1 into the negative x squared into the I alpha x dx. Okay, so this is not something that you can easily do. And actually, I think the convolution is not easy as well. But so this is equal to the convolution G1 star G2. Right. The Fourier transform of the product is the convolution of the Fourier transforms. Okay, so this is why did I write P? I meant alpha here. So this is C squared root of pi convolution negative infinity to infinity e to negative alpha squared root of 4 sine, well, not alpha, let's say beta, some variable we're integrating over, alpha minus beta over alpha minus beta d beta. Yeah, so in this case, this turns out not to be easy to solve as well. So I guess it's not that great. But you get the idea, right? In some cases that yeah. But yeah, it's just the ease for calculating Fourier transform f1, f2, or g1, g2. Yeah, it's for that. Yeah, for this class, I think convolution. The only way we apply convolution is to find the inverse transforms and stuff like this. Okay, any questions? All right, and I guess that's it then. See you on
Thank you guys.
Tuesday.
Will we check in on her Zoom or which Zoom do we check in for the final?
The Zoom, I'm not sure. Well, I think we'll send out an email
Right.
over the weekend.
Thank you, guys.
Nice. So let me stop recording.
So long.
Yeah. What is it?